as we study the chemical sciences, we often find that we would like to specify the amount of substance in a given sample. In day-to-day terms, we often use words like 1 dozen bananas, meaning 12 bananas, 1 kilogram wheat, meaning the mass of the wheat that we are talking about is 1 kilogram. It is often helpful and useful to specify the amount of a substance, and hence we need metrics or parameters via which we can do so. One such parameter is the mole. The mole is nothing but as many entities as are present in 12 grams of carbon 12 isotope. So we look at the carbon atom and we take 12 grams of carbon atoms and see how many entities or atoms are present inside it. And those many entities are called as 1 mole. So essentially 1 mole experimentally or empirically comes out to be equal to 6.023 into 10 raised to 23. This is also called as the Avogadro number. Let me put an approximate sign over here because we are obviously truncating the decimals. It's not exactly 6.023 into 10 raised to 23. It might be slightly more or less, but for regular chemical equations and day-to-day calculations, this is the value that we are going to use. Let me write down the definition of what 1 mole is. 1 mole is an amount of substance that has as many entities. Okay, so let's write down as many entities. What is the meaning of entities over here? I'll write down in bracket. Entities may mean species or atoms or molecules or ions or electrons or protons or neutrons or anything. So entity is what we define it to be in that particular context or that particular problem as we are solving it. Hence, 1 mole of bananas would be 6.023 into 10 raised to 23 bananas. 1 mole of humans would be 6.023 into 10 raised to 23 humans. 1 mole of planets would be 6.023 into 10 raised to 23 planets, so on and so forth. Okay. As many entities as are present in 12 grams of the carbon 12 isotope. As many entities as are present in 12 grams of carbon 12 isotope. Now, what is the logic or the rationale behind defining exactly this value to be 1 mole of entities? So there is a rationale behind that. See, we have defined gram to be the day-to-day usage term for measuring mass in small quantities. In our day-to-day life, gram is a relevant unit. And we would like to answer the question, how many protons would essentially measure equivalent to 1 gram, or how many protons would constitute 1 gram of mass? And that leads us to the answer 6.023 into 10 raised to 23. So let's see how. The mass of one proton is 1.6 into 10 raised to minus 27 kgs. That means this is equal to 1.6. This is the mass of a proton. This is equal to 1.6 into 10 raised to minus 24 grams. Now when we multiply the mass of a proton by the Avogadro number, I invite the student to figure it out that when we do this, we are going to get the equivalent of 1 gram. Or else, if we divide, alternatively, if we divide 1 gram with the mass of a proton, then we are going to get the Avogadro number. And hence, the concept of mole has been initiated to pin down a number which represents the number of protons present in 1 gram. Similarly, we could have chosen the neutron instead of the proton and we would get a very similar value of the Avogadro number, because the mass of the neutron is approximately same as the mass of the proton. So essentially speaking, 1 mole represents the number of protons present in 1 gram of any substance. And this is the exact reason why this quantity mole is important.